tutorial, let us make like this. Whatever query you have, you write in a paper. And if you do not have a loose paper, then we can give you loose paper as well. So write in a paper and then give to the volunteer, and I will give that paper to him, because so that there is no communication gap. Write in clear sentence or clear word, and we both will be answering your query. So queries means it is not that solution of problem. Queries means to clear the concept. That is more important. You have seen that in his lecture how nicely he is dealt with light, molecule and interaction. So this approach is a very fantastic approach, because if you understand in this way, then dealing with spectroscope is very easy. But understanding in that way, you need to involve more and more time, because lots of derivation is involved. And this is one approach. Another approach is that the way I told you that as a bird's eye view, Raman spectroscopy means what is a scattering, two types of scattering. This is a bird's eye view. So it is always, in my opinion, it is always better to have a bird's eye view first, so that you understand where you are standing, and then you try to go into depth. So see it first superficially from the top, and then you discuss, try to understand that one and in depth, means cell level mein. Okay? So you can discuss. There is no bad question. There is nothing like a good question, bad question. Division is not there. If the answer of that question helps you to clear any doubt, that means you are the gainer. And when you ask some question, remember, most of the students have lack of understanding of that one. So if you ask, that means you are helping others, because they will be listening the answer. So feel free to ask the question. You have 1 hour time. You can have discussion according to your understanding. Okay? You do not worry about whether your understanding is wrong or right. Just ask, which will clear your doubts. Okay? So let us start from who will be the first one. You can ask the question directly, or you can write the question and hand over the question. Okay, another thing is that we have to give you the grade card. Grade card means we have to take the examination, we have to give marks, so we have to evaluate your performance. So if you ask the question, that also will be a part of the evaluation. So we will mark it that you are actively participating. So we will get marks, even if you are not performing that one in the written one, but this will add up. So this you remembered. So participate in the discussion. First one, okay.
Good afternoon, sir. So in the light matter interaction portion, we have introduced a force term. So what is the significance of that force term?
So that is the interaction itself. So it's an interaction itself, that is. So when there is a charge and there is an electric field, there occurs some force and nothing else. So the interaction force is the most important origin of the light matter interaction.
So like without the force term, we cannot basically derive the Hamiltonian part, right?
Without force, nothing happens, so it goes as it is.
Okay.
Nothing happens.
Okay.
So no absorption, no scattering.
Okay. Sir. And one more question was from that, yes, where we introduced the vector potential A. Like, could you explain it a bit easier? Like, what is vector potential A? Why are we using it?
So the vector potential is a function that generates the vector by the operation. So that's it. So we assume the same origin for the E and B.
Oh, so
But-
it's a origin. Okay.
Origin.
Okay.
So virtual origin. So
Okay.
convenient function.
Okay, sir. Thank you.
Hello. I have a follow-up question to the force term that she asked. I wanted to know if the force applied as the result of the electric field and the magnetic field is the only basis of interaction between the light and matter, or there is possibility of any other interaction?
Actually, what do you expect?
Like as electromagnetic radiation, the electric field and the magnetic field, as the molecule is charged, so these electric and magnetic field, of course, they will have like a force on the charged molecule itself
Right,
when we
right.
irradiate with light. So that
Both originates the interaction. So
yeah.
we need to consider the contribution from E and B both.
Okay, yes. And so I wanted to know is what happens to the overall Hamiltonian of the interaction if on top of the electromagnetic radiation we apply some external field?
External electric field.
Yes,
You mean the static electric field?
yes.
Okay. It would give some additional term. Besides
okay.
electromagnetic field, you may apply the external electric field. Then some change in the orientation may occur.
Yeah.
So
Will that allow us to probe the molecules' energy states? Those are not accessible by only the electromagnetic wave if we apply some external electric field, or
so the intensity is quite different.
yeah.
Intensity of the electric field is quite different between the light electric field and static electric field. Also, the frequency is different. And so,
Okay. The other question that I have is while formulating for the irradiation light, you derived the equation as the minimum value of energy for light to be h cross omega and k gamma for the Planck's photon hypothesis. If you remember, the minimum energy. Yeah. So I was wondering, there was a term like n, a quantum number plus half of h cross omega k gamma.
Yep.
So I was wondering how that half like didn't come up to be included in the minimum energy.
how can I say? You may learn how to describe the Schrödinger equation of the one-dimensional harmonic oscillator. So there appears half 1/2 term
Yes.
in the energy.
Yes.
So if the energy is 0, then how can I say? If without half term, we can determine the position and velocity or energy at the same time. So it is contradiction to the uncertainty principle. So always half term appears, and
Yes. So half term should appear, right?
right.
Yes. But okay, in your slide, it was only h cross omega k gamma. So I was wondering if there should be a half term or not.
Just a moment. Just a moment. There must be, and probably I omitted.
Okay. Okay.
So,
So your question or your query is that Stokes shift and anti-Stokes shift.
Yes, sir.
Now, this slide, this is the energy level representation, and this is how the spectrum appears. So let us first understand this one. Say you have this is a rotational Raman spectroscopy, that is why J 0, 1, 2, and the selection rule says delta J plus minus 2. So you will have a transition. This is not the Raman, so leave it. So if your molecule is in ground state, here, this is the ground state. if your molecule is in ground state and it goes to the excited state out of the interaction with the light, where it will go, whether here or here, it depends how much light you are giving. Say it is going to the virtual state 0. Okay. So this is not a real electronic state, or not a state that actually is there in the molecule. So this is a virtual state. So you are rising the molecule here, and instantly it comes down, and it comes down to a rotational energy level where there is a difference of delta J plus 2. So this is 0, this is 2. So the difference delta J is plus 2. So it comes here. So now you have a loss of energy between the excitation wavelength and what you are getting. So this is the loss of energy. So this energy appears in the spectrum here.
Okay, sir.
So these energies appear in the spectrum. So here in Stokes, you start from the originating ground state, and in anti-Stoke, your molecule always will have a population of excited state according to the Boltzmann distribution. So if your molecule is in this state, excited state, J is equal to 2, and then it goes to another virtual state, and it will come back to the state following the selection rule. In this case also delta J minus 2. So this difference is appearing as a band in anti-Stoke region. So this is the Rayleigh band because of this one, and this one is the Stokes one because of this, and this one is because of this. So your Raman spectrum usually appears. I will show you one spectrum that one of your senior has recorded, this one. This is recorded by one of my student when he was doing MSc with our professor, his PhD professor, my postdoc professor, Professor Hamaguchi. He recorded this one. This is a rotational Raman spectrum of H2 and 3.2 atmosphere mixed with HD. So this is a rotational Raman. So here you expect this 0, Raman shift 0. This is the place where you should have a very strong Rayleigh scattering. So they have eliminated using some special optics which doesn't allow the excitation light to go into the detector. And in addition to that, again you will have some amount, maybe residual one, that he has eliminated by some mathematical operation. So that is why it is like this. So this is the Rayleigh position, and this side is anti-Stoke minus anti-Stokes. Minus has as such no meaning in energy. There is nothing like energy minus. It's just this side is minus, anti-Stoke, this is plus. Now this is a real spectrum I am talking about. So you see the first band appears because of the transition. What's transition? 0 to 2. So first band is appearing because of this difference. So 0 to 2, that appears in 354 nanometer, a wave number. 354 wave number. This is 354 wave number. 0 to 2. And in this one, 220, this also should be 354, and it is indeed 354. So this is like that. Likewise, the second band will be 321. Difference should be always 2. This also 123. 123, difference is 2. So this second band appears at 587 wave number. Here 587 wave number. So difference is that intensity is the difference. Yes. The intensity is the difference. As such, we do not record anti-Stoke part. We record always the Stokes one, unless you have some specific reason. One of the specific reason is that if you record both Stokes and anti-Stokes, by the comparing the this area of this area of this Stokes band, a anti-Stokes band, with the area of same Stokes band, then you can calculate the energy, calculate the temperature of the molecule. So this is the temperature of the molecule. It is not a temperature of the whole ensemble system. It is the temperature of the molecule. So comparing these two intensity of the same band, so you can get the temperature of the molecule. In that case, you have to record both Stokes and anti-Stokes. Otherwise, we record only a Stokes side, because anti-Stokes is usually very weak intensity. Okay?
Thank you, sir.
What is yours one?
Sir, I have a little misconception. You have told that in Raman spectroscopy, it is applicable even for the non-dipole molecules such as N2O2, CO2, C2, sorry. Then will it be
C2
considered
means what kind of molecule? C2?
like non-dipole moments which don't have any dipole, like electronegativity difference and all?
But is there any molecule C2?
Sorry, sir. O2 and N2, okay.
Uh-huh.
And then will it be considered as the discardation of dipole moment and polarization, like the rule? Whenever we calculate the dipole moment, it is always considered that there should be the difference between electronegativity. Then only we can calculate the dipole moment. But you said that in Raman spectroscopy, we can calculate the dipole moment and polarization of the non-dipole molecules too.
Okay. So this O2, N2 as such, they do not, this is a spherical molecule, they do not get separated. O and O connected. We cannot expect that there will be difference of charge between the two parts. No? But when you are using an electric field, then there is an induced dipole moment generated. This is induced dipole moment. This is not the permanent dipole moment in the molecule.
Then what is the meaning of alpha over there? Like, it is showing the polarizability.
Yes, alpha is the polarizability, and that polarizability depends on how much light you are giving. What is the amplitude of that, intensity of that oscillating electric field?
Okay, sir. Thank you, sir.
Any question for me? So their roll number, you collect their roll number. Yeah? Bolo. Separation between the lines. No, ideally, yes. No, there should be some 4b plus 6dq, no? Separation between. Yes, yes. No, it depends. It depends if you are considering Born-Oppenheimer approximation valid or invalid. If you are considering that this Born-Oppenheimer approximation is valid, that means your B0 and B1 and B2 all are same, then it will be the same spacing. Otherwise, this PQR, that band, will, one side it will increase, another side it will decrease.
So, but we are observing the trend in decreasing the order, that it is completely decreasing from today in the Stokes time. So, is there any specific reason?
In case of, say,
So, we are seeing a continuous trend that it is separation is decreasing.
one side it will be decreasing.
Linearly. It is decreasing.
Yes,
linearly.
yes, yes, yes.
Any specific reason for that?
For that, you can have this this consideration of Born-Oppenheimer approximation. If you consider that B0, B1, B2, they are the same, there is no change in that bond length, then there will be only fixed difference. Otherwise, there will be change in that. In one side it will increase, another side it will decrease. Maybe tomorrow I will discuss this one in case of IR. Huh? You have anything to say?
Harmonicity? So, in the case of harmonic oscillation, spacing of the vibration must be the same. But when the H2 molecule oscillates, it looks like harmonic oscillator. But what happens if it goes so far? It does not return, it goes away. So this is dissociation potential. So the potential should not be always harmonic, it should be flat. So in that sense, harmonic potential is valid when the vibration level is near 0, 1, 2, and if it goes to higher level, energy state becomes denser. So transition frequency becomes smaller. So I think this is due to unharmonicity of the potential of H2 molecule.
So different types of spectroscopy include vibrational, rotational. So sir, is it only based on mobility of molecules and its spectra? So the spectroscopy of molecules and their spectra? Yes sir. So like,
Maybe you are the right.
so different type of spectroscopy including vibrational, rotational, translation. So is it only based on mobility of molecules and their spectra?
So there is no translational spectroscopy,
So vibrational and rotational.
right?
Yes sir.
And in the gas phase, they can rotate freely,
Okay.
and vibration vibrate freely. So they can define the rotational level 0, 1, 2 energy level. So it's possible to detect rotational transition
So
in the
are
gas
you able to
phase.
say that only on mobility of molecules, like any other aspect? So that rotational or vibration? So that rotational and vibrational thing, like rotating and vibrating.
Right?
Yes, sir.
It's not separable, not separable.
Not separable. Okay.
V0, V1 and R0, R0, or V0, V1, R0, R2, or several levels.
Okay.
And
Yes, sir. My question is based on the Raman spectroscopy in the light and molecule interaction. You were mentioned there that molecules, particles should be charged for light matter interaction. Is it necessary to molecule to be charged for and how is it differ? How is it differ for the charged molecule Hamiltonian and neutral particle Hamiltonian?
so your question is about the charged molecule and neutral molecule.
Yes.
Even if we pick up a neutral molecule, it consists of carbon, hydrogen, oxygen, and hydrogen is consists of the positive nucleus and electron. So overall, it may be neutral, but each particle electron is negatively charged, nucleus is positively charged. So there is no neutral, only neutron is neutral, but atomic nuclei must be positively charged. So there is no neutral particle. Overall, it may be neutral, but each atom interacts with the field. That's it.
Okay. Thank you.
On the basis of their molecular print. For me, it should be same.
Could you explain again?
Okay. Raman spectroscopy can distinguish between two isomers, but for me, their chemical formula is same. So the molecular print we will see in the form of spectra will be same. So how we will be distinguished on the basis of their spectra?
So what kind of isomer do you consider?
Like any isomers, because in case of isomers the chemical formula is same, so the, as far as I know, the Raman spectroscopy deals with the stretching and the chemical formula is same, so how it will be distinguished on the basis of the spectra?
So in the case of 1,2-dichloroethane, you know, CH2Cl, CH2Cl, direction of Cl may be trans or gauche 02. Then the vibration of CCl stretching couples constructively when gauche in the gauche form construct in this same phase. But so in the case of opposite trans structure, vibration becomes different. The overall displacement of the atoms are different. So the vibration frequency becomes different and intensity different. Accordingly, spectral pattern becomes different. So
You are saying with respect to their configuration, whether it is cis or trans, the energy in their vibrational state will change. That will be detected by the spectrum. Like in the form of their peaks, the intensity peaks, or in the form of their bandwidth.
So peak position must be different. Also intensity must be different. And bandwidth origin of the bandwidth is related to the lifetime of the vibration. So usually it's almost the same in many cases. So peak position is mainly different.
Thank you, sir.
So isotopes, you talked about isotopes or isomers? Isomers. Raman spectroscopy is a very popular technique for polymorphism, studies of polymorphism.
So, while converting the classical mechanics into quantum mechanical approach in the formulation of light, you used annihilation operator and creation operator. For annihilation operator, you mentioned that it decreases one photon having the value k and gamma. Okay. So, I want you to know what is the physical meaning of decreasing one photon.
It's absorption of light.
So the annihilation operator basically means if molecule will absorb.
So how can I say? Annihilation operator is applied to the wave function of the light and affects the number of photons. So it reduces one. That is a mathematical equation, but physical meaning corresponds to decrease in the number of photons. So it is absorption of light. Light is absorbed, so the number of photons decreases.
And then increasing one photon means
Emission.
emitting. It is related to a particular state or a particular eigenstate.
So at this stage, there is no information about NK gamma. So some photon decrease. That's it. There, and so how can I say? So when we proceed the formulation, we can explain the absorption process with that formulation, and energy difference to the real state should be related. But at this stage, no explanation.
Sir, I have a question regarding the occupation number representation of psi. Sir, why you are using it and what are the benefits of, like, I want to know the mathematics behind it.
Sorry, why I'm
Why?
using
Yes,
that
sir.
expression?
Yes, sir.
It's because it's simple, easy. So as far as we regard light is oscillating wave, and we can use the formulation for the one-dimensional oscillator. So about the wave function and energy. So wave function form is always given by the normalization coefficient, element polynomial, and exponential functions. So it's unique by specifying n quantum number or k gamma. And energy is also uniquely determined by the nk gamma. So nk gamma is convenient parameter to specify all both function and energy state. So only by specifying which k gamma, how many photon, which k gamma, how many photon, by listing the number of photons, and we can uniquely describe what is the wave function of the light. So that's why we use such a convenient equation. Okay, so no other information necessary in that regard.
So it is kind of a simplified version. So it is basically it explains the it explains more simplifically.
So it's convenient to describe what is the absorption. Photon number of photon decreases, absorption. Number of photon increases, that is emission. Or one photon disappears, one photon appears, that is scattering. So it's convenient. So we introduce that expression. What is that?
Sir, I have one more question regarding the describing A, vector A, E and B. Quantum mechanically, you said that we are setting up the coordinates like k q gamma equal to k q gamma plus q star k gamma. So why you are doing that?
K Q
Gamma plus k q star gamma.
Q K gamma star
Yes.
is equal to large Q.
Yes, sir.
So actually, this is not my finding. So it's convenient way to describe, so derive the further equations. So I can say, because it's convenient.
Okay, sir. Thank you, sir.
Yeah. Just a moment. So when the vibration motion decay, so in particular in the liquid phase, in the gas phase, when the vibration starts, there is no obstruction, so frequent vibration continues long time. On the other hand, in the liquid phase, it dumps in a finite time. Okay, so this damping oscillation is expressed by considering the oscillating function multiplied by exponential decay. So that function, the product of the oscillating function and the exponential decay, is Fourier transformed. Then it becomes Lorentzian curve. On the other hand, when the Gaussian function appears, when the Lorentzian function gathers to some extent. So if there is some multiplicity, then band shape becomes Gaussian curve. So the underlying mechanism of the decay, underlying reason is different. Lorentzian curve occurs from damping oscillation. Gaussian curve is due to some multiple distribution, in my understanding. Irrespective of the geometry, some vibration mode must be Raman active, depending on the symmetry group. So you will find some Raman band, Raman active vibration of any molecule, I guess.
I also know any molecule you should find some. Is there any molecule he wants to? Is there any molecule which is not Raman active because of the geometry?
Noble gas.
Noble gas.
Sir, I want to ask a basic question that we know that when we are giving a single excitation source like 532 nanometer or 633, there is a Stokes band and anti-Stokes band at the same position. So why does it is at a same position? So is it as the Boltzmann distribution, there is no the number of population at the excitation state, it's not known. So how it comes at the same same Raman shift in case of both Stokes and anti-Stokes?
So the both indicate the energy spacing between V0 and V1 state, irrespective of the starting point. If the starting point is 0, then it moves to 1, and energy spacing between 0 and 1 will be detected. If the starting point is 1, then the anti-Stokes line final is 0, so spacing between 0 and 1 will be detected. So it must be exactly the same.
So why it starts from 1?
So when there is a population in the vibrational excited state, V1 state, it occurs. V1 to V2 also occurs. So how can I say it? So usually the population depends on the temperature, and ratio of the V0 and V1 state depends on the temperature and obeys the Boltzmann distribution. So usually lower energy state is high and largely populated than the upper state. So the thermal temperature at room temperature corresponds to 200 wave number. So less than 200 wave number, there is a not negligible population in the higher state. So we can have a larger chance to detect the transition from V1 to V0 state, anti-Stokes line. But above 200 wave number, almost 100% populates in V0 state. So we have almost no chance to detect the anti-Stokes line. But anyway, when we excite with blue laser, scattered light is blue. When we excite with red laser, scattered light must be red. And energy difference is constant. And it corresponds to V0, V1 spacing, irrespective of starting point. So it must be always the same.
So if it starts from V2 or V3, can't it come to V1 or V2 according to the...
So the vibrational quantum number should change only one.
Yeah. So if it starts from V2, so can it become to V1?
There is a possibility
Yeah.
V2 to V1 anti-Stokes line will be observed. But the contribution must be much smaller than V1, V0 transition.
Thank you.
Okay.
No, this one, I have told you that this difference matters. So for any specific example of rotational spectroscopy, rotational Raman, where delta J is plus minus 2, with this selection rule, your transition will happen. So if it starts from the ground state and it will come back to a state, the end point will be in such that this selection rule is satisfied. So this is same for, it will come here, so the energy difference is this one. This is the energy difference. And anti-Stokes, if you consider that it is starting from j is equal to 2, it goes to the another virtual state and it will come back to the ground state. The difference is same. Since this difference indicates the energy level, this energy level is same, that's why in this energy scale, they will appear in the same place. And the intensity part depends on the population. So population of the excited state depends on the Boltzmann distribution. So Boltzmann distribution says for, say, vibrational energy level, if you consider 100 molecules in V0, then less than 1 molecule will be in the V1 state. So that's why this excited state, from transition from the excited state and then getting the difference, this becomes much more less. He is asking what will be the effect of weak interactions like hydrogen bonding interactions on Raman spectrum.
So, in the case the hydrogen bonding occurs, then, for example, let's consider there is a OH group, and hydrogen of the OH group is attracted by another oxygen of water, in the case of protein. Then what happens? OH bond length should be longer because of the attraction by another oxygen. Accordingly, the distance between the original OH bond becomes longer and force constant becomes smaller. Then the lower peak shift occurs, vibration frequency becomes smaller. And this hydrogen bonding is various. Oxygen comes from this side or this side or this side, and distance between hydrogen and new oxygen is various. So the effect on this OH bond is various. Accordingly, the OH stretching frequency is shifted. So, and each OH stretching gives a band, but there is multiple structures. So it broadens the band. Okay. So, in the case of low frequency mode, less than 200 wave number, at 25 degrees, both Stokes and anti-Stokes lines should appear. At lower temperature, V1 population becomes 0, and 100% is populated to V0. So there must be no anti-Stokes line, only Stokes line should appear.
In order to get better resolution, we go for signal to noise ratio, but we can't increase the signal to an extent, and we also cannot decrease the noise ratio, the noise part. So what is the criteria we should go for in order to get a good resolution in Raman spectroscopy?
Resolution should be determined for the purpose of the experiment, not to consider, and do not consider SN ratio. Okay, so if you want to separate these crossing adjacent two peaks, you need to make the entrance slit smaller for better resolution. Accordingly, SN ratio would be lower. So you need to accumulate longer time. If you do not need to separate these two adjacent peaks, then you may make it larger. So it depends on the purpose. So in my experience, I did an experiment with the resolution of 32 wave number in IR spectroscopy, only to detect delta absorbance, to use to detect larger number of photons.
Sir, if I'm increasing the time span, there will be effect of photo bleaching as well. So it will be interfering with my experiment now. Like, I don't want it to hamper my experiment as well. Because of the photo bleaching, I won't be able to see the structural changes that is actually happening. So,
Then you should spend the time.
okay. In like I should be checking every aspect, like signal to noise ratio, in order to get the best image or whatever I am desiring of, like what structural analysis I am thinking of.
So first, please fix the entrance slit resolution for your purpose. Then check the photo stability and fix the laser power. Then automatically the SN ratio per unit time will be fixed. Then you can decide how long time you need to spend. Okay.
Thank you, sir.
So he wants to say that first you decide your purpose, and if your say 1 millijoule power is giving the photo bleaching, then you have to fix it less than 1 millijoule, say 0.5 millijoule is good for your experiment. So laser power is fixed, and then along with that you fix the slit width also. What is the minimum slit width which is not giving you the bleaching? So then these two is fixed. Now the SN ratio depends on your how much time you are using for accumulation. So if your time permits, you can accumulate for 1000 spectrum. So that's why he wants to say that it depends on your purpose. You have to fix one by one, and then say sometime we have to record one spectrum, say hours together. Sometime in one shot, within few seconds it comes. So in his case, he said that 32 wave number is the resolution. 32 wave number is is not well resolved, but his purpose is served in that. He wants to identify some new spaces. That new spaces band is coming. So in there is bandwidth is not a problem. That is you get signal, get the existence of that species. So your purpose should decide what kind of conditions you will keep for your experiment. Yeah, that is called Raman imaging. Yeah, usually live cell imaging is done based on the fluorescence, but Raman imaging is much better in the sense that Raman image is based on the molecular vibration. So you pick up a vibrational mode, like your molecule has a ketone group. So you see where are the presence of ketone group in your whole biological cell. So if you see a ketone group and that ketone group is because of one molecule A, then you monitor the ketone group in the whole biological cell, and then you can say these are the distribution of ketone group. So this is gives you much more crispier image than the fluorescence one. But for that you need to have a normal Raman machine cannot do that one, because you need to have a piezo stage, and imaging software.
You also mentioned that signal to noise ratio should be in the form of root. In the form of root.
I mentioned that signal to noise ratio means S by N. So if you increase the number of recording to 10 times, then your signal increases by 10 times, but noise increases by root 10 times. So 10 by root 10 is equal to root 10. So you are gaining signal to noise by root 10 times. No, it's just example. If it is 4 by root 4, 2, 4 by 2, 2. So you are gaining by 2.